Welcome everyone to this 11th lecture of States of Matter. Myself Varad Daoo. I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous classes, we have seen about kinetic theory of gases and the limitations of it. Then building upon these limitations, we studied the van der Waals gas equation, uh, right? And then we also studied that van der Waals gas equation basically represents the equation for real gases and it's a cubic equation of it, right? So in this class, we are going to study about liquefaction of gases into the critical phenomena. We are going to study about the uh, critical temperature, critical pressure, right? And then we are going to study about continuity of state. Then further, we are going to quantify this critical constant, namely the critical temperature, critical pressure, and critical volume in terms of van der Waals constant. Further, we are going to delve deeper into liquid state of matter, and then we are going to study about the basic properties of liquid state. And then finally, we'll study about the other properties of liquid such as evaporation and vapor pressure, right? So let us start. So this is lecture 11, states of matter. The first topic which we are going to study is critical pressure. We are going to study is liquefaction of gases and the critical phenomena. Liquefaction of gases and critical phenomenon, right? So gases can be liquefied by lowering the temperature and increasing the pressure, right? We are all aware that gases can be liquefied by decreasing decreasing temperature or increasing pressure, right? In the middle of 19th century, a number of gases such as carbon dioxide, sulfur dioxide, and etc. were liquefied by combined effect of cooling, that is lowering the temperature as well as increasing the pressure. According to kinetic molecular model of gases, the forces of attraction between the molecules are negligible. When the temperature of the gas is lowered, the kinetic energy of the molecule decreases. As a result, the slow moving molecules come near to one another. At a sufficiently low temperature, some of the slow moving molecules cannot resist the force of attraction and they come closer and closer, and ultimately the gas changes into liquid state. The increasing pressure can also bring the gaseous molecule closer to one another due to decrease in volume. Therefore, the gases can be liquefied by increasing the pressure. Thus, gases can be liquefied by decrease of temperature or increase of pressure or the combined effects of both. Right? So let us write this down. Right? According to kinetic molecular theory of gases, according to kinetic theory of gases, the force of attraction between the molecules are negligible. The force of attraction between molecules are negligible. Right? When the temperature of the gas is lower, then the temperature of the gas is lowered, the kinetic energy of the molecule decreases. The kinetic energy of the molecules decreases, right? As a result of what? As a result of this, the forces of attraction between the molecules dominates, right? The kinetic energy of the molecule decreases. As a result, the slow moving molecule come closer to another. As a result, the slow moving molecules, the slow moving molecules, the slow moving molecules come near to one another. Come near to one another. Right? At a sufficiently low temperature, some of the slow moving molecules cannot resist the forces of attraction. At a sufficiently low temperature, sufficiently low temperature, some of the slow moving molecules, some of the slow moving molecules, some of the slow moving molecules cannot resist the forces of attraction. Cannot resist forces of attraction. And they come closer and closer ultimately. And they come closer and closer ultimately until and ultimately the gas changes into liquid state. The gas changes into liquid state, right? The increase in pressure can also bring the gaseous molecule close to one another. The increase in pressure can also bring molecules close to one another, right? Therefore, the gases can be liquefied by increase of pressure also. Therefore, gases can be liquefied by increasing pressure also, right? Thus, gases can be liquefied by decrease of temperature, or increase of pressure, or combined effect of both, right? However, the effect of temperature is rather important than the pressure, right? The essential condition for liquefaction of gases was studied by Thomson and Andrews in 1869, right? So, however, the effect of temperature is rather more important than more important than the pressure, right? And the essential conditions for for liquefaction of gases was studied by Andrew Thomas Andrews in 1869, right? Thomas Andrews studied the pressure volume temperature relationship in gases and liquid states of carbon dioxide. He measured the variation of volume of CO2 with pressure at various constant temperature and plotted the isotherms of CO2 gas at different pressure. And these plots can be seen as like this. So these were the plots which we have obtained. So as you can see in here, the y-axis denotes the pressure and the x-axis denotes the volume, and each corresponding line is an isotherm, right? So that means it's a constant pressure. So this is isotherm. Isotherms means the temperature is going to remain the constant, right? Right. So this shows the plot of pressure versus volume for CO2 at a constant temperature obtained by plotting the Andrews data. Andrews observed that at high temperature, isotherm look like that of an ideal gas, and the gas cannot be liquefied even at very high pressure. As the temperature is lowered, the shape of the curve changes, and data shows more and more deviation from ideal behavior. This is because CO2 does not behave ideally as the temperature becomes lower and lower. Right? So let us write this down from the figure present on next page. We observe that the first point which you observe is at high temperature, at high temperature, isotherm look like that of an ideal gas. Isotherm for CO2 looks like that of an ideal gas, and the gas cannot be liquefied, and the gas cannot be liquefied even at very high pressure, even at very high pressure, right? Further, as the temperature is lower, as the temperature is lower, the shape of the curve changes. The shape of the curve changes, and data shows more and more deviation. Data shows more and more deviations from ideality, right? And this is because CO2 does not behave ideally, does not behave ideally as the temperature becomes lower and lower. As the temperature becomes lower and lower. Right? From this figure, at 50 degrees centigrade, there is this isotherm. From this isotherm, the for CO2 is this isotherm of for CO2 is very similar to that of an ideal gas. It was observed that at temperature T is equals to 30.98 degrees centigrade, carbon dioxide remains gas up to 73 atmospheric pressure, right? As shown by point x, right? As shown by point x here. This is the highest temperature at which liquid carbon dioxide is observed. Above this temperature, it is gas, and this temperature is called as critical temperature. Further increase in pressure simply compresses the liquid carbon dioxide, and the curve represents the compressibility of that liquid. It is observed that even a slight compression results in steep rise in pressure, indicating a very low compressibility of the liquid. Right? Let us write this down. It is clear from the figure that the isotherm for CO2, isotherm for CO2 is very similar to that of is very similar to that of the ideal gas. So it was observed that it can be observed that at 30.98 degrees centigrade, carbon dioxide remains gas, CO2 remains gas up to 73 atm, up to 73 atm, right? As shown in point X, right? At 73 atm pressure, liquid carbon dioxide appears for the first time. Liquid CO2 appears for the first time, right? This is the highest temperature at which this is the highest temperature at which this is the highest temperature at which liquid carbon dioxide is observed. Liquid CO2 is observed, right? And above this temperature, it is gas. Above this temperature, it is gas, and this point is called as critical temperature. This temperature is called as critical temperature, right? Further increasing pressure simply compresses the liquid. Further increase in pressure simply compresses the liquid CO2. Simply compresses the liquid CO2, and the curve represents the compressibility of the liquid. Compressibility of the liquid, right? It is observed that even a slight compression, it can be observed that even a slight compression results in steep rise in pressure, indicating very low compressibility of the liquid, right? Below 30.98 degrees centigrade, the behavior of the curve on compression is quite different, right? For example, at 21.5 degrees centigrade, right? At this temperature, with 28.5 degrees centigrade, somewhere around here, right? What we observe that the isotherm ABCD consists of three parts. At point A, the carbon dioxide is a gas, and the volume of the gas decreases along AB as the pressure increases to point B, right? As the pressure increases up to point B, right? As the pressure increases up to point B, then what happens? At point B, liquid of particular volume appears, right? At point B, the liquid of particular volume appears. Further compression does not change the pressure. Liquid and gaseous carbon dioxide coexist, and further application of pressure results in condensation of more gas until point C is reached, right? This point, this line. So the horizontal portion BC indicates that there is a considerable change in volume with a change in pressure indicating process of liquefaction. In other words, the gas condenses to a compact liquid. The condensation would be completed at this point, point C. At C, when the condensation is complete, the isotherm rises sharply as there is very little change in the volume of the liquid as pressure increases. In other words, the reduction in volume from C to D corresponds to very high pressure required to compress a liquid into a smaller volume. Right? From this figure, we also see that a slight compression from volume V2 to V3 results in a steep rise in pressure from P2 to P3. Right? So let us write this down. Below 30.98 degrees centigrade, the behavior of the gas, the behavior of the gas on compression is quite different. Is quite different. For example, at 20.5 degrees centigrade, the isotherm ABCD consists of three parts. At point A, CO2 is in gas state. CO2 is gas, and the volume of the gas decreases along AB as pressure increases up to B, right? At B, liquid of particular volume appears. Liquid of particular volume appears. Further compression does not change the pressure. Further compression does not change the volume. Further does not change the pressure. Right? Liquid and gaseous carbon dioxide coexist. Liquid and gaseous CO2 coexist, and further application of pressure, further application of pressure, further application of pressure results in the condensation of more gas, results in the condensation of more gas until point C is reached, right? Until point C is reached, right? So the horizontal portion BC indicates, so the horizontal portion BC indicates that there is considerable change in volume, that there is considerable change in volume, that there is considerable change in volume with a change in pressure indicating, with a change in pressure indicating process of liquefaction, process of liquefaction, right? In other words, the gas condenses to a compact liquid. In other words, gas condenses into compact liquid, right? The condensation would be completed at point C. Okay. The condensation would be completed at point C. At C, when the condensation is complete, the isotherm rises sharply. At C, when condensation is complete, the isotherm rises sharply, right? At C, when the condensation is completed, the isotherm rises steeply as there is very little change in the volume, as there is little change in volume, very little change in volume of the liquid as pressure increases very steeply, right? As pressure increases. In other words, the reduction in volume from C to D, in other words, reduction in volume from C to D corresponds to very high, corresponds to very high, corresponds to very high pressure required to, very high pressure required to compress a liquid into smaller volume, compress liquid into smaller volume. Below 30.98 degrees centigrade, that is the critical temperature, each curve shows the similar trend, except that the length of the horizontal line decreases at lower temperature, right? We observe that the horizontal portion becomes smaller as the temperature increases. At critical point, the horizontal portion of the curve merges into one point. Thus, we can say that a point like A in figure, in the below figure, represents a gaseous state. A point like D represents liquid state, right? So let us write down a point like A represents gaseous state. right? Then a point like D represents liquid state, and a point under the dash shape area, and a point under a dash shape area under the dash shape area represents coexistence of liquid and solid, liquid and vapor, coexistence of liquid and gas, right? Andrews also concluded that all gases under the compression at constant temperature, that is isothermal compression, show the behavior similar to the behavior of carbon dioxide. Thus, we observe that at 30.98 degrees centigrade, the isotherm has a very small flat portion, virtually reduced to a point X. Above 30.98 degrees centigrade, there is no flat portion, indicating that under all pressure, it remains a gaseous state. Generally, the gases below their critical temperatures are called as vapors, right? Gases below their critical temperature are called as vapors, right? Thus, Andrews concluded that there is a certain temperature above which a gas cannot be liquefied no matter how high a pressure may be applied. The gas can be liquefied only below this temperature, and this characteristic temperature is called critical temperature, right? So, thus, Andrews concluded that there is a certain temperature, that there is a certain temperature above which a gas cannot be liquefied no matter how high a pressure may be applied, how high a pressure may be applied, the gas can only be liquefied below this temperature, below this temperature, right? And this characteristic temperature temperature is called as critical temperature and is denoted as Tc, T subscript C. Thus, the critical temperature is the temperature above which is the temperature above which a gas cannot be liquefied. A gas cannot be liquefied, however high the pressure may be. However high the pressure may be, right? For example, the critical temperature of carbon dioxide is found out to be 31.1 degrees centigrade, right? So, Tc for CO2 has been found out to be 31.1 degrees centigrade. This means that the carbon dioxide cannot be liquefied above this temperature, even at a pressure of several hundred atmospheric pressure. Similarly, critical pressure and critical volume may be defined as, okay, similarly, critical volume, critical pressure Pc, and critical volume may be defined as critical pressure is the minimum pressure. Critical pressure is the minimum pressure required to required to liquefy the gas at critical temperature. Gas at critical temperature, right? And critical volume is the volume. Critical volume is the volume occupied by 1 mole of the gas at critical temperature and pressure. And pressure. Okay, so importance of critical temperature is gases like helium, hydrogen, and nitrogen cannot be liquefied at ordinary temperatures by increasing the pressure alone, however high it may be. Such gases are called as permanent gases. Right? It is possible to convert a gas into liquid or a liquid into a gas by a process in which only a single state is always present. Right? So let us understand this. Continuity of state. Continuity of state. Right? It is possible to convert a gas into a liquid or liquid into a gas by a process in which only a single state is always present. On joining the ends of the horizontal portion of various isotopes, a boundary curve, which is nothing but represented by the shaded portion, is obtained. It has critical point X at its top within the area of boundary curve. Both liquid and gaseous states can coexist, but outside this area, only one phase, either liquid or gas alone, can exist. Right? So it is possible to convert a gas into liquid and vice versa by a process in which only a single state is always present. Single state is always present. Right? On joining the ends of the horizontal portions of various isotopes, a boundary curve KGCXPFI represented by the shaded portion is obtained. Right? It has critical point. It has critical point X at its top. Right? Within the area of the boundary curve, within the area of the boundary curve, both liquid and gaseous states can coexist. Both liquid and gaseous states can coexist, but outside this area, only one phase, either liquid or gases, can exist. At critical temperature, liquid changes into gaseous state interceptually and continuously and the surface separating these two phases disappears. A gas below its critical temperature can be liquefied by applying pressure and is called vapor of the substances. Right? At critical temperature. At critical temperature, liquid changes into gaseous state, state imperceptibly, and continuously, and and the surface separating these two, and the surface separating these two phases disappears. This appears. A gas below its critical temperature is called as vapor of the substance. Right? At critical point, the densities of the substances in liquid and gaseous state becomes equal. At critical point, what we have is the separation or the separation line or the phase line between liquid and gaseous state represents disappears. Hence, we cannot distinguish between liquid and gaseous state. Hence, the property, the interface vanishes, and hence we can say that the density of the liquid at critical point, right, becomes equal to density of gas at critical point. And there is no distinction between gas state and liquid state. No second phase is formed irrespective of the pressure of the system. It may be noted that the dense fluid obtained by compressing a gas when its temperature is higher than its critical temperature is not a true liquid, but it behaves like a liquid in many aspects, right? However, it is strictly a liquid because it never possesses a surface area which separates it from the liquid phase. These fluids above the critical temperature are called as supercritical fluids. The fluids above the critical temperature are called as supercritical fluids. Right? And in terms of, right, critical constants, in terms of, now the next topic is critical constants and van der Waals equation of state. Right? So critical constant Tc in terms of van der Waals coefficient can be given as this 8a by 27 Rb. For Pc, it corresponds to a by 27 b square, and for Bc, it is 3b. Right? Alternatively, if Pc, Vc, and Tc of gas is known, it is possible to calculate the values of B. Right? So B is going to be Vc by 3. Then A is going to be 3 PCVC square, and R is going to be 8 PCVC by 3 DC. Right? And then the boil temperature, which we have studied in the previous classes, right? Boil temperature TB in terms of van der Waals constant can be given as TB is equals to A by BR. Right? So these are very important expressions which we must remember. Okay? So in this class, what we have studied about the critical liquefaction of gases and the critical phenomena. We have seen that this critical there exists a critical temperature, and the critical temperature is the temperature above which a gas cannot be liquefied, however high the pressure may be. Further, we have also studied about the critical pressure and critical volume. Then we have also studied about the continuity of state, right? And at the end, we have studied about the supercritical fluid and the critical constant in terms of van der Waals equation, right? In the next class, we are going to go into detail about liquid state of matter and we are going to study various properties of liquid such as its density, volume, compressibility, evaporation and vapor pressure, and surface tension and viscosity. Right? I hope you have enjoyed this class, and I hope all you all to see you again in the next class. Thank you.